Hi everyone, I'm very glad to see you. So the topic of our talk is Beyond the Cluster, One Data Replication with GridGain. My name is Yakov Zdanov. I work for GridGain for quite a bit. I'm Apache Ignite committee and PMC member. Have some passion for performance and scalability, always find a way to make our product better. I live in St. Petersburg, Russia, so I think everyone notices this accent. Okay, let's go. So here is our plan. We'll start with a short discussion of why we replicate our data. Then we'll take a look on how databases solve this problem. Then we'll take a small comparison of replication problem in monolith versus distributed systems. And then we'll have an overview of the current state of this functionality in GridGain. And then I will share some future plans which are under development now. So this is TX replication. So why we replicate the data? First of all, data replication makes our data more secure. So if we replicate our data set, we have another copy of data, or probably even more copies. So if one copy gets corrupted due to some reason, so we can easily recover from redundant copies. Another point is failover. So when one installation of our data gets down due to some reason, then we can fail over our service to another database or another service or data service without significant downtime or without any service interruption at all. Another point is data warehousing. So we can offload the main service and free some resources to run analytical processing on the data, on copies of our data. Another point is load balancing. So if we replicate the simple, very simple but very valuable addition to the system, it may be so that we can run read queries over replicas, while write queries will be processed by subset or one server throughout all our installation. We're also increasing system capacity with this trick. Okay, let's see how PostgreSQL handles the replication problem. I choose this database because it's very mature, it's open source and widely used in many variety of deployments. Okay, so first thing that PostgreSQL offers us is just a shared storage. So we have one server, one database server which writes to the network attached disks, and another standby server which will mount this storage server in case of first server failure, and therefore we will not have any interruption of the service. So second server will pick the data up and start a new database instance. So this can be thought of some kind of restart for the first server. Another option is file system replication. In this approach, we are suggested to replicate all the changes on the file system of server A to file system of server B. Here, a very important point is that all the changes should be done in the same order. So the order they appear on server B should be the same as order on server A. This will make sure that we have consistent data on both servers, and once we have a need to do so, server B can be easily brought up and start serving the requests. So probably the most popular way to set up the replication is write-ahead log shipping. So primary instance just forwards the write-ahead logs to the standby instances, and this is probably the most popular. thing to do the replication, and the only limitation is that this to be required to replicate the whole database server. You cannot replicate some tables individually. So logical replication allows you to fetch some logical changes from the write-ahead log statements and stream them to your standby servers. Trigger-based master standby replication. This is based also on the approach when master node sends the updates to the standby servers. And in this solution, by the way, standby servers can handle the read-only queries, but only with the condition that master server is still running. Statement-based replication middleware. So this is very interesting one, I think. So you can set it up by intercepting every SQL query coming to your system, and then write queries which can probably modify data. They are sent to all of the servers, and queries that are read-only, they are sent to some random server, and the result should be consistent. The only probably problematic point of this approach is that functions like current timestamp or random or like functions of the kind, they can return different results, so we need to be careful about that, not to corrupt our data if it is sensitive from business logic standpoint. I think multi-master replication and sync multi-master replication, they're pretty much complex and challenging, so I would not stop on them for too much. So here in this table I've gathered all these points which from my opinion are critical for monolith system when we choose to go with a replication, and I was trying to think over whether those points are valid for distributed systems or not. So first of all, data security. So when it comes to monolithic systems, then data security is increased without a doubt when we add more replicas to our database server. But when it comes to distributed system, this probably does not help too much, because if we take, let's say, Apache Ignite or any other system of the kind, so we just can add backup count to our cluster, and therefore we have more redundant copies of data. So failover, that's definitely a plus for distributed system, because if we have all the whole cluster shut down and we have the copy of the data in another cluster, then we can switch all the clients to work with the secondary clusters without service interruption or significant downtimes. When it comes to load balancing, well, here I'm not sure about this particular point, because I think there are a lot of techniques just to make load balancing inside single cluster, and there's probably no point of starting a few more clusters. But for monolith systems, this is definitely a plus. As far as increasing system capacity, I think that distributed system like Apache Ignite or GridGain, we can increase system capacity by just simply adding more servers, more RAM, more cores to our single cluster. No point just I can increase capacity a lot by adding by strengthening my single cluster. And as far as data warehousing, I think that currently any system of Apache Ignite kind is pretty much ready for HTOP hybrid workloads. So that's probably, in my view, does not make too much sense for distributed system. Nevertheless, so failovers stays a very important point from my point of view. And there can be also some reasons like latencies and for data requests. I mean, imagine the situation when you have clients of your data service through all over the globe, and you just do the start different data centers in different areas, for example, in Europe, North America, and Asia, and set up replication between them just to make sure that latencies for your clients are kept to minimum. That's probably a good point I missed here in this table, but I would give a plus for both from monolith and distributed systems here. Okay, so what about replication in GridGain? So first of all, I'm not sure about the date when it was first introduced. I think it was like 2013. It was completely new feature and required a lot of engineering efforts, and even from the point that we were required to revisit a lot of code related to existing logic which has already been set up and tested. So we changed some critical parts of the system with which some of the changes were pretty critical. For now, we have only asynchronous key value mode available. Key value mode means that we do not honor transactions here. So if you update key 1 and key 2 in one data center, in data center 1 in the same transaction, they can probably show up in different order or in different updates within data center 2. But this is just simplification for us to make the implementation a little bit more easier. Currently, we are working on synchronous and asynchronous TX replication. We are in the progress, let's say, of some kind of preparation. We are building the MVCC functionality now, which will be critical for which will be critical for TX replication. So, okay, let's go and discuss some definitions that will help us throughout the presentation. So, imagine we have two clusters with the bidirectional replication set up between them. So, imagine we do some data modification puts here with data modification calls. Here, this may be the DML SQL statement or cache API invocation such as put or remove. So we need to define the sender cache. This is the cache, data modification of which are replicated to its replicas. So they are replicated via the sender hubs of the sending topology. So sender cache sends the batches to the sender hub. Sender hub sends them to receiver hub on the receiving topology, and the batch processing should end by applying the whole batch to the receiver cache, which means that when I do get on this topology from this cache, or I do SQL query, I will get the results that were modified on this in this cluster. Quick feature overview. So currently we support complex topology up to 32 data centers. I think that even 32 is pretty much overhead, so probably we'll never go up several data centers, but still it was not very hard to do. Important thing to mention that we managed to fill all this information about data centers, about versioning, about state of the cluster to the cache version object, which I think was too primitive longs I mean the object that contained two primitive longs inside. So we just cut several bits to save the data center information, and therefore we did not make it bigger. So when it comes to millions and billions of keys and values in the data center or in the cache, key value pairs in the cache, so we did not affect the total data size. We support complex failover scenarios, so any component of our system, we survive the failure of nodes in sender and receiving topologies. So we also support filtering, which means that you can decide on what caches, what keys, and what values are replicated. So you have an ability to pause and resume the replication process, and you also have an ability to do a full state transfer, which means that the whole state in one data center will be moved to another data center. This can be helpful when we have just set up the replication process, and let's say data center 2 is currently empty while data center 1 has already working data set. Okay, so here we have the diagram explaining how replication process works in a bit more detail. So when we do data modification call on this data center, which actually any data modification call resolves to some set of nodes, to the primary node and backup nodes, which are responsible for storing the primary copy for that key and the backup copies for that particular key. So here on primary nodes and on backup nodes, all the updates are organized in batches, and batches can be sent to the sender hub by per time basis or per size basis. So when batch grows too big, we send it. When time's running out for the batch, we send it as well. Then what is important here is that all the components of this data center, all the servers are still GridGain nodes. So sender hub is still a GridGain node, which shares the same information of topology, and it's just a node with a special role. So, okay, once the batch is sent to the sender hub, it is stored to the persistent queue, and then sender hub acknowledges the batch for the primary node, and the primary node removes the acknowledged batch from its storage. So this, if sorry, so then sender hub sends the batch to the receiving cluster, and receiving cluster applies the batch on the local topology. You see that topology can be different. This is not a requirement to have mirrored installation. You can have like different numbers of servers, different servers of different power, different capacity, and still everything should work. So imagine if we have a data modification call here, which sets value v1 to the same key. Then we will have to involve the conflict resolution process, which is pluggable, or you can rely to an automatic conflict resolution process that comes out of the box. Actually, if you choose to implement your own conflict resolver, you can choose what version of the value should we use, what version of the value we should use. I mean, you can choose either V1 or V, or even build a merge of those two values depending on your business logic. So when it comes to complex topologies, this was some imaginary example that is still possible. So we support bidirectional replication, and we also can detect loops. So data modified here will be going here and here and here, but will never go back here because we track all the information. The information about the data center that originated the update is stored in the version, and the version of that key will be the same throughout this topology, unless you not overwrite it with conflict resolver. Then if as a result of the conflict resolution it changed, then we will have to replicate it back, and here you will have another value for this key. Okay, so when it comes to distributed systems, then everything can go wrong, like with every component of the system. So let's see what do we do in some failure scenarios. So the first failure scenario is node failure in sending topology. So at some point this node is considered as failed. So this is a recoverable situation. So we will send the batches to the sender hub from the backup nodes. So none of the batches will be lost. So if this node dies before sending acknowledge to the client, then client will get an exception, which means that the transaction should be retried one more time. And if a client has got a successful acknowledge that transaction, that data changing operation has been committed, then it means that all the backups have all the data copies, and therefore we can use the information on backups to send them to the sender hubs, and system will hardly notice this failure. So this is 100% recoverable situation, unless we do not experience data loss. So in this case, we lose, let's say, all the servers that hold some copy of the partition. So partition is totally lost, then this situation will not be recovered. But this is some kind of showstopper for any critical app. So this will need to be reviewed by people who run the system and to recover manually recovered. Okay, what about sender hubs failure? So if one sender hubs fail, then we have another sender hub which can take over, and I think they work. No, they work in parallel. So when we lose one sender hub and we have redundancy between them, then we probably will not notice this failure. If we do not have redundancy between sender hubs, and losing one sender hub will make batches persisted on this sender hub and have not been sent yet to another topology, temporarily unavailable, which means that we need to fix the machine that ran it and restart the process, and once it is restarted, all the batches will be sent to the receiving topologies. If in the case we lost all the sender hubs in this topology, so this makes our replication impossible, and nodes will be continuing to collect batches until some limit, and once they have free memory. But once the memory is over, the replication batch collection will be stopped, and the system-wide error flag will be set up. So we will have to do a full state transfer once we have our sender hubs online. Receiver hub failures. So this is pretty much the same as with sender hubs, but it's probably a little bit less affecting because receiver hub does not have any persistent data structure like sender hub does. So if this guy was processing a batch and has not sent the acknowledge back to sender hubs he received the batch from, then batch transition will be repeated to another sender hub. Once all sender hubs are offline, then this topology will be considered offline for this topology, and will be periodically checked whether we can establish a new connection or not. Node failure in receiving topology. This is pretty much the same as node failure in sending topology and should be pretty much unnoticeable. So we seamlessly recover and apply this batch and reapply this batch on the new primary node, which will be picked up on the receiving topology. So currently we are batching on per node basis, which I think is not a 100% optimal solution, because per node batching to my opinion, so per node batching is a little bit not optimal. So and I would suggest that we switch at some point to per partition batching. So when the batches come from all the partitions that were that node on the sending topologies was responsible for, then we need to have additional processing on receiving side. But if I know in advance that all my entries are belonging to the same partition, then there would be no need for additional processing on the receiving side. I just can take this batch, I resolve the affinity node for that batch, I send this batch to that particular node. So there will probably reduce contention, because this approach 100% honors the thread per partition model. Probably this will lead to high GC pressure due to bigger amount of smaller objects in the Java heaps of the process, but I still expect this to perform faster. There are also probably we will need to have a bit more networking calls, but okay, we'll see when we implement this. I will share the results. Okay, so when it comes to transaction replication, so everything I explained before was related to key value replication, which does not own a transaction, and your updates can show up in the backup cluster in different order or in different sets, which will not be reflecting the order and state of changes in the sending topology. And once the sending topology fails, you will have the new cluster that will be consistent from data standpoint, and data will be available for service failover. But what if, so currently we don't have such a functionality, but this can be easily worked around it if I create a stretched cluster over 2 data centers. So imagine this is my first data center, and this one is my second data center. They are linked with they should be probably have a decent link between them with a decent bandwidth and low latency, but we'll need it in any case, even if we are not building the stretched cluster, but all the same. So I would suggest, so we implement a special affinity function that will spread the primary nodes throughout the primary partitions throughout the whole cluster, and have backups for the partitions that are primary here. We will have backups, let's say here, and for partitions that are primary in this part of our cluster, we will have backups in this cluster. So clusters, once we have a split, then we will have all the data consistent in both parts of our cluster. In any case, so we are considering implementing the transaction replication, and this will be implemented in the following way. So first of all, to solve this problem, we need to have a global transaction order in the sending topology. So once we have this, then we will then it will be much easier, not much easier, but it will be at least possible for us to restore the transaction ordering, the updates ordering in the receiving topology. So all the data chunks will still be sent to the sender hubs, and data chunk, so this, the changes will be holding the information about the partition number, partition sequence, and whether this change touch one partition or touch several partitions. So also each partition will have an update sequence, and once batches arrive here to the receiving topology, we will check the first we'll check that the partition sequence in the batch is, let's say, the next one to the current state of that partition in the receiving topology, so we can easily apply that batch. That means that we do not have any space in between, so we will not be missing any update. Another point is that we will need to check whether transaction was touching single partition on the sending topology or it was touching several partitions. Then we will just spread this check through several partition on receiving topology. But basically the mechanism will stay pretty much the same, so we will have the sending topology, sender hubs and receiver topology as well. About replication modes, that synchronization modes that we are planning to support. If the first one is strict sync mode, which means that commit acknowledge will be sent to the client that initiated the initial update on the sending topology only when the changes are applied to the cache of the receiver topology. To the so then when we go through all this chain and go back, so then we issue the acknowledge to the client that initiated the update operation. So this is this will probably be pretty much the same as this case, which I explained. So with a full sync transaction, guarantees, when client gets the control back only when the primary and backup copies are fully updated, then this strict sync mode can be considered as an equivalent for full synchronization mode. Okay, merciful sync mode. This is a little bit more relaxed, and we just wait for an acknowledge from the receiver topology, receiver hub, and for a sync mode we just wait for an update on the sender hub. So this is still subject to change. Probably this will change at some point, but for now the vision is the same as on this slide. Okay. What do we learn throughout this talk? So when considering to set up a replication, so we need to answer the question, first of all, is replication able to solve our problem? So in some points, you probably better to add servers to your single cluster, or to play with some data distribution or request processing inside your cluster. So if we come to the replication, we should pick up proper settings, so sync versus async, and or physical versus logical changes. And we should always be aware of the internals. We should know what makes our system work and what mechanism working behind the scenes. So we also need to make sure everything is properly tested, tuned, and is under constant monitoring. So here is the email. If you have any questions, do not hesitate to contact me. Also, here is I invite everyone to participate in our open source community. Here is the site for Apache Ignite, and here are the mailing lists which I invite you to participate in. Thank you very much. Any questions? Welcome.
Why don't you use HTTPS protocol?
Okay, I will fix it now. Okay, yes, that's very valuable comment. I will fix it for sure. HTTP versus HTTPS.
Yeah, you see, we are working on a very similar, Alexander Budnik from EPAM system, we are working on a very similar solution which include transaction replications and with application of replicas on a receiver side in parallel. So we're trying to use a dependency, resolve dependency between transaction scopes. So if you're interested, please, let me know.
No, but okay, thank you very much. But I didn't say that we use sequential updates. So we will be applying the batches in parallel, but only if, so there will be no like transaction spanning different partitions. So you will not be able to just,
no,
you will lose the sequence of updates.
Yeah, I'm talking about like a node level replication, because at node level, the all transaction happens in one node, right?
Of course.
I mean, in a thread local of that node. And as I understand, on a key level, you may miss the sequences if you don't support versions of the key. Let's see, we put a value 5 for key 3, and then value 7 for key 3 as well. And it's not guaranteed that you receive updates in the same order, right?
Yes, it is not guaranteed, so you can receive value 7, but you can still receive all the updates, because you can, I think there is a trick, so you can switch your cluster to have always conflict resolution. I mean, whenever the update comes, so so your situation is that first value 7 arrives, then and it gets applied, and then value 3 arrives, and when we resolve conflicts automatically, we see that both updates were originated from the same data center, and version is monotonously growing. Therefore, we can just ignore value 5 for that key, but you can switch the mode of conflict resolution to always, which means you will be your conflict resolver will always be notified, and therefore you will get the updates in different order, but you have an opportunity not to miss any update.
And I believe that monotonity on version numbers is not enough. It should be also one by one, I mean, without any gaps, or have links between them. Other way you can miss something in between.
Yeah, but yeah, and I understand what you're talking about. So I think it's better to continue.
That's, I think it's a clear sign.
Yeah.
So, question: any specific optimizations for copying the data across between two data centers geographically distributed across leased lines, meaning like lower bandwidth lines.
Excuse me, I didn't get that. Can you please repeat?
Do you envision any specific optimizations when you try to distribute the data between data centers which are located in different geographical areas, like geographical countries, and your bandwidth is limited because the lines between different countries are leased?
Yeah. Okay. So, well, if I have, let's say, 1 terabit per second of incoming traffic to data center number 1, and all this data should be stored on data center 1, then not to afford any significant delays, I has to be able to push all this data to my replicas. If my bandwidth or my links does not allow to do that, then the gap will be growing and growing and growing. So there no way to resolve it. The only way is probably if you have some peak hours, and let's say this peak hours you have very significant incoming traffic, and you cannot push through. So this time you allow gap to appear and to grow, but then when peak hours are finished, let's say everyone goes to sleep, the stocks are closed or something like that, so you will have an opportunity to reduce that gap or fully eliminate it.
I forgot to ask, did you cover the situation of...
No, but Alexander, I'm sorry.
I'm sorry.
You assume that every change must be immediately propagated to the other class.
No, I didn't say that.
So that the latency can be like several seconds. You can batch updates. You can, for example, compress the updates.
Yeah, even if I do it, and but still the incoming data is. I mean, incoming traffic that needs to be stored in data center 1 is much, it cannot fit to the link that I have between these two data centers. Then there is no solution at all. So we will not be ready to push all this traffic through that link. Of course, compression and probably some logical pre-processing can help, but we still need to pick up another link if the gap keeps growing.
I don't remember that you cover a situation when the link is getting shut down for a time, okay. And then you have to do like a reconciliation, or maybe the whole data center, like a receiving data center could be down for some time.
There actually was a slide which explained the situation when a receiver hub is failed, and also if all the receiver hub are failed, this
same as a link.
Yes,
right?
I don't distinguish this situation from
it's
the
different
links.
Because if you have a load balancer which spread the load between the data centers, or even your link is down, load balancer may not know about that and continue sending updates through from application to the second data center, right?
No, but this probably needs to be solved on that balancer level. So it needs to be intellectual enough to have proper decision.
Make a load balancer use the same link.
As a solution.
It's fun.
You had said that you can do a full state transfer. I'm curious how long that takes. If you had like 18 gigabytes in your data center 1 and your data center 2 was empty and you did a full state transfer, what's your guess on how long that might take?
That's again the speed, the current load of my cluster, the current traffic in my cluster, how much room I have in my network inside this cluster, how fast is my link, what is the bandwidth of my link, and yes, and also I probably, I'm sorry, I forgot to mention the situation that if the link is down and batches started to accumulate here in the persistent queue, probably it is cheaper just to discard all of them and do a full state transfer, because when it comes to the updates, I mean, when data gets constantly updated, not new values inserted, but the updates, then we probably will have the whole data set in this cluster less than the size of our persistent queues.
One more question. Do you have like a special initial sync mode?
So the question is whether we have special initial sync mode. I'm trying to understand.
Let's say you put a new cluster in the production and
Oh.
it's completely empty.
So you do full state transfer from the cluster?
Is it special mode for the application? Or
No, it says from management console.
Okay, I see. So there is a mode called full set transfer. Oh, full state transfer.
So if no more questions left, thank you very much. Thank you for coming. Goodbye.